You're about to enter into the motion part of parametrics problems, and most of the AP style questions involving parametrics are going to involve motion since that seems to be the best application of these things. So most of the motion type of things that you have to answer in these style problems is going to depend upon your knowledge of the motion fundamentals from AB calculus, which is why hopefully you took the time to study the quick motion review that we had in the lesson plans a few days ago. I'm going to hit the highlights of things that might be different or added onto when you're using the parametrics. First of all, you've had access to and hopefully have watched a previous video showing you how the vectors are going to be the way that you're going to display most of the information of position, velocity, and acceleration. So make sure you're up on that vector idea and go back and revisit that previous video if you haven't yet. The next thing to look at is the speed, which unfortunately you're going to have to memorize that this is going to give you the speed of an object. Now this is supposing that we have a position function or a vector x of t comma y of t, and the derivative of x and the derivative of y are what's happening inside of this square root to get you speed. And this speed calculation, although it looks like it's a little rough to memorize, it has some logic behind it. It's deeper logic than what I'm about to tell you, but let's just think of it this way. If we were in the regular old equations before you knew anything about parametrics, speed was the absolute value of velocity. Well, the derivative of position is velocity, so you can tell that's a velocity component, and that's a velocity component. And when you square them, they become positive. And when you square root it, you're getting rid of the square. So this is actually quite a fancy way of saying absolute value is always going to be positive. And that may or may not help you. If it doesn't help you, then just go back and memorize that thing because that's what you're going to have to do. One thing to also know, speed is sometimes called the magnitude of velocity. In other words, velocity is going to have a sign, plus or minus, but the magnitude is the actual number of your velocity. For example, a velocity of negative 73 has a magnitude of 73. So they will use the term speed and magnitude of velocity interchangeably. In the note packet that you have on the lesson plans, and you're probably also in possession of it, there's a section as soon as we start the motion part that goes over this speed information. But since you have that and you have access to this note packet already filled out, I'm not going to go ahead and reread that for you. The next thing that you're going to want to have to unfortunately memorize and put into the brain is distance traveled. And your distance traveled is going to be an integral, and it's a big old ugly thing. Well, first of all, let's notice this is really that. And let's think about why this could make sense to memorize. Before you were in parametrics, you knew that the integral of the absolute value of velocity is the distance traveled. And by the way, just for a refresher, the absolute value, or the integral of just plain old velocity, is displacement. But that's not really what we're talking about right now. Well, if the integral of the absolute value of velocity was distance traveled, this is the integral of, and since this is the speed that you're going to memorize up there, and speed is the absolute value of velocity, this is really this, just updated for parametrics form. So it seems like we would have two different things to memorize, but they really are the same thing. and they really are relying upon concepts that you knew from back in the old motion days. I've transferred back to that motion packet to show you that there is distance traveled information on that note packet, and it's easy for you to read it if you need it. I'm going to take a few moments to point out a few other things in the motion part of the notes packet. This part down here, which is at the bottom of the first page of the motion part, it's basically giving you a more visual look at the vectors. So I'm just going to highlight one vector location. At t equals -1, these notes lead you to figure out a dx dt and a dy dt. So dx dt and dy dt are the velocity portions of the vector. So we have a velocity vector of -2, 2 at t equals -1. Okay, so we need to find out where that is on this graph, and it turns out that that point is right there. That's the t equals -1. If you're wondering how we know that that's the location at t equals 1, remember, as you read through here, you have a position function or a position vector, and that would be, oops, that's off on the side, sorry. That position vector tells me that that's my position. Then at t equals -1, that velocity vector, -2, 2, and to remind you of what this means, a velocity vector of -2 for the horizontal component tells me it's heading 2 units that way to the left, to the negative, and 2 units upward. So that would go 2 units upward, and that makes that blue arrow the net effect of traveling to the left and upward. That arrow is a visual representation of that velocity vector. Continuing through that same notes packet, you have an example up here with speed. Unfortunately, that's just the application of that formula you would memorize. And down here, you have a slightly more involved problem. In this problem, you're making a velocity vector, no big deal. In this part, they talk about the time when the particle intersects the x-axis. One thing you should remember, if a particle is dancing around la da 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 and intercepts the x-axis, it would intercept the x-axis when the y portion of vector, the y portion of the position vector was 0. By the way, it would intercept the x-axis when the x component of the position vector is 0. And then the ending example in these notes is a distance traveled of a particle, and the distance traveled is really just an application of the arc length formula of parametric equations, and it's what we talked about at the beginning of this video as well. A final point I would like to make is a lot of your learning about the motion in parametrics is going to come from you completing these homework problems that we have on the homework sheet, all relating to motion, starting at 13 and going through number 27. You really wouldn't want a set of notes that was so long and comprehensive that it covers every little nook and cranny that you might find, which is why it's important that you're completing this homework and checking your solutions and asking questions about what you don't understand. All right, this was a rambling video, but I think we got a lot covered, and that should be the last video I have to do about motion in parametrics. Talk to you later. Bye.